Okay, we now go to post-order traversal. So post-order traversal is different from pre-order traversal, and the difference is here which recursive calls are made first. So first we check, this is slide number 4. So first you check whether the tree is empty. If not, then you do the recursive traversal in the following way. You perform a post-order traversal of the left subtree, then perform a post-order traversal of the right subtree, and then visit the root of t. So you can see the tree here, which is the same tree actually, and here these are the nodes. I'll not perhaps draw the entire tree, but just to give you a flavor, you can see the tree in the lecture slide. So here you can see the idea is to first perform a post-order traversal of the left subtree. So I'm not going to print the this particular node first, because my aim is to first go down to the left subtree. So I go down to the left subtree here, I go down further, I go down further, and there is nowhere to go now. So now I write the 1 here. And then I have to traverse the right subtree. So I come back and I go down here and print here. And now I have completed the traversal of this entire subtree except for the root node. So what is at the root node? The plus. So hence I print the plus. Now I go back from there, and I'm not going to print the multiplication symbol. Rather, I go down to the right subtree of this, and which is the number 3, and then I come back and write the multiplication symbol. So that is the idea. And next I go back again because I have nowhere to go. So I go back here and go to the right subtree of the root node. And from there I go to the left subtrees recursively until I can go no further. And that is why you can see that first 4, then 5, then the multiplication symbol, which is here, is printed. This was 4, this was 5. And then I go back here. This node was storing a minus, and this node was storing 6. But I have to come here at the very end. So I first go to the right subtree and print the 6 minus, which is this node here, and then we go back to the root and print the plus. So this is the post-order traversal. And the in-order traversal, we have come to now slide number 5, the in-order traversal, where the order of traversal is different. Here again you check whether the tree is empty or not, perform in-order traversal of the left subtree completely, then visit the root, then perform the in-order traversal of the right subtree. So again we start from the tree here, which is the root node plus, and it has a left subtree which has a root node multiplication. But you see the way we traverse the tree is perform first the in-order traversal of the left subtree. So we have to go down and down the left subtree, and you can see I am going further down, and now I have nowhere to go, so I print the 1, and then I print the root. The root in this case is this node here, so I print the plus sorry, and then I go down the right subtree, which is 2, and then I go back to the root of this big subtree, which is the multiplication, and go to the right subtree of that, which is 3, and so on. So you won't have much difficulty in recreating the rest of the traversal. So these are the 3 traversals, 3 depth first traversals. Slide number 6, which is the level order or breadth-first traversal. Here what I do is I exhaust all the nodes level by level. So I first start off from the root, I print the root, then the two children of the root are the node storing the multiplication and the node storing the minus. So I completely exhaust this level. Then I have other nodes here. I exhaust all the nodes here and so on. So that is why it is called level order traversal. So you can look at the algorithm at slide number 7, where while queue is not empty, place the tree root in empty, use a queue, auxiliary queue, and then you just traverse it, first the root, then the left subtree and the right subtree. So that is the level order traversal. Now what is the complexity? Slide number 8 here. I just went through slide number 7 because you won't have any difficulty in following it. The analysis of traversal, the time complexity is order n time for a binary tree of size n, because every node you are touching once. Whatever may be your traversal algorithm, actually some of the depth first traversals you are touching a node 2 times, once while going down and once while going up. But anyway, it is order n. So you cannot improve upon the asymptotic complexity. Slide number 9, what is the space complexity of traversal? In depth first, recursive implementation requires memory, which we have discussed in one of the workshops because of the recursive calls, which is proportional to the height of the tree. Worst case, size n implies height of n. Expected case, the height is order of log n, or log n colloquially we say, but there is a hidden constant. In level order traversal, you have to remember which trees are yet to be processed. That is the next slide. I am talking about slide number 10 now. In level order, you have to remember that is why you are using an auxiliary queue, and that increases the space complexity a little bit more, again linear in size of the tree. Okay, slide number 11, breadth first graph search. Breadth first search in a graph is a little more complicated than a level order traversal of a tree, because we must make sure that we do not visit the same node twice. Because you see, in a tree there is an advantage that there are only one unique path between any pair of nodes. But in a graph there are many different ways of reaching a node, and that is why we have to be careful that we don't traverse a node unnecessarily. And breadth first search is a simple but extremely important technique for searching a graph. This search technique starts from a given vertex V and constructs a spanning tree for G. A spanning tree basically extracts a subgraph from a tree so that the tree property is valid and also every node is traversed. Now for that we use a queue, and you know that in slide 12 we know the standard operations in a queue are the push and pop operations. So here is the breadth first search initialization. Here is basically the initialization for a graph. What we do is we use some colors. Now the idea of a color is not really a real color like red, blue, green, etc., but to associate an integer. It's a common terminology in graph algorithms to call them as colors. So initially, when the search hasn't started, we mark the color of every vertex as white and the queue is empty. Now, what we'll do is we will remember in the queue the vertices that we need to explore further. And when we reach a particular vertex V, we color it with gray, and we remember the parent of that vertex. It's easy to remember because we know from where we have reached that vertex, and that is how we store the parent information pi of V, and that is how we get the tree, because for a tree we need to know from where we can go where, which vertex is reached from which vertex. Now you can see that in slide number, that was slide number 13, slide number 14, we have the code for breadth-first search. I'm not writing the code. The idea is to push V. You can arbitrarily choose a vertex to start your breadth-first search, push V onto the tail of Q, that is at the push it in the Q. While Q is not empty, pop vertex W from the head of Q. You take the vertex out, whichever vertex is at the front of the queue, you take it out. For each vertex X adjacent to W, the vertex that you are taking out, there are other vertices adjacent to it. Here is the trick. If color of X is white, we are talking about a vertex W and a vertex X that is adjacent to W. If color of X is white, if this is white, that means we have not reached this vertex yet. Then what we remember is that the parent of X is W, because we have reached X from W. That is the parent information. And also we make X gray, because gray color indicates that we have now seen this vertex for the first time. And now we push X to the end of our queue. So there is a queue, we push it at the end to indicate that we have to explore this vertex in future. And that's why that's what we continue doing for all the vertices that are adjacent to W. And when we have done that same process, what we did for X, for each of these vertices, then we are done. And we come back and mark W as black. That means W is done now. There is nothing more to do for W. Now notice that all these vertices as well as X, they have now gone into this queue. And hence, we'll next pop the vertices from the queue one by one and continue this process. Now, I'll not go through the simulation that is in the slides. You can go through the simulation and you can see how this is happening and how the colors of the vertices are changing. And at the end, we have all the parent information. All the vertices have been colored black. If you look at the last slide of this demonstration sequence, and everyone has a parent information except for the vertex where we started, because the vertex where we started doesn't have any parent information. Its parent is undefined. So at termination of breadth-first search, I'm talking about the slide that is actually slide number 22 perhaps here, where the end of the example ends, and at termination, that heading of the slide. At the termination of breadth-first search, every vertex in the same connected component as V is a black vertex, and the array pi contains details of a spanning tree for that component, the breadth-first tree. What is the time analysis? Time analysis is order of V plus E. Actually, it is both a lower bound and an upper bound. Why V plus E? Because we have to touch every vertex and we have to explore every edge. Remember, we followed the edges and looked at the adjacent vertices. Next slide is uses of BFS. Breadth-first search is particularly useful for certain simple tasks such as determining whether a graph is connected or finding the distance between two vertices. If the graph is not connected, there are multiple components in the graph, then you will get multiple breadth-first trees.